Welcome back to DeepVisus, where vision meets depth. I'm your host, and today we're diving into an exciting exploration of neural field models from a fascinating source, the book Neural Fields, Theory and Applications, edited by Stephen Coombes, beim Graben, Roland Potthast, and James Wright. In this episode, we'll focus on chapters 6 and 7, which delve into the complex dynamics of neural fields, including the intriguing concepts of spatial delays and the behavior of localized activity patterns. Now, you might be wondering, how do localized activity patterns, or spots, form and evolve within neural fields? And what happens when these spots interact or even move? These are the questions we'll be exploring in today's review. So let's break it down and see how neural fields give rise to some of the most fascinating dynamics in neuroscience. Let's begin with Chapter 6, where we're introduced to the concept of neural fields and the importance of space-dependent delays. The chapter, titled Numerical Simulation Scheme of One and Two-Dimensional Neural Fields Involving Space-Dependent Delays, addresses how finite transmission speeds along axons, the long fibers in neurons, affect the spread of neural activity. You see, neurons communicate with each other, but the speed at which signals travel along these axons isn't instantaneous. And this creates delays, meaning that activity at one location will be influenced by what happened earlier at another location. This delay is especially important in systems that involve large-scale neural networks, like in the brain. Chapter 6 introduces a novel numerical scheme to handle these delays in two-dimensional neural fields. By using a method that involves both spatial and temporal integration, the authors were able to speed up simulations by a factor of 10 to 20, making it feasible to simulate these systems in a reasonable amount of time. With this approach, they were able to observe how patterns of activity, known as breathers, emerge due to these transmission delays. So, how do delays in neural activity affect pattern formation in the brain? The answer lies in this new numerical approach, allowing us to simulate the spread of activity over space and time. This work ultimately shows that transmission delays can lead to complex dynamics, like the formation of breathers, which are oscillating, localized patterns in neural activity. Now, let's move on to Chapter 7, which expands on the idea of localized activity, but this time, we focus on the behavior of these localized solutions, or spots, in a neural field model with spike frequency adaptation. Chapter 7, titled Spots, Breathing, Drifting, and Scattering in a Neural Field Model, takes us into the realm of two-dimensional spots that can breathe, drift, or even scatter. The chapter introduces a two-dimensional neural field model that includes both short-range excitation and long-range inhibition between neurons. These interactions give rise to localized activity patterns, or spots, that can either remain stationary, oscillate in time, breathers, or even move across the field, drifting spots. The authors explore how spike frequency adaptation, which is a mechanism where the firing rate of neurons adjusts over time, influences these spots. For example, a stable spot can transition into a periodic breather when it undergoes a Hopf bifurcation, a type of instability that leads to oscillations. Similarly, when parameters like the strength of inhibition or adaptation are adjusted, the spot can shift to a drifting spot, essentially moving across the neural field. To understand these phenomena, the authors use numerical simulations and bifurcation analysis to track the evolution of these spots. One particularly interesting aspect of their work is how spots interact. They found that when two spots approach each other, they can reflect off each other in a way that's similar to how solitons, or localized waves, behave in other physical systems. So, after diving into chapters 6 and 7, we've learned that neural fields, with their intricate delays and local interactions, form the perfect stage for observing localized patterns like spots. Whether these spots stay stationary, oscillate in time as breathers, or move as drifting spots, they reveal much about the complex dynamics of neural systems. The introduction of spike frequency adaptation and the analysis of their bifurcations gives us valuable insight into how the brain might organize and regulate its own neural activity. And to answer our initial question, how do these spots behave when they interact or move? Well, the answer is fascinating. These spots can drift, collide, and even scatter like solitons, leading to new patterns of neural dynamics. This behavior could be crucial for understanding how localized activity in the brain interacts and spreads across regions, influencing cognitive functions like memory. As we wrap up today's review, you might be wondering what other complex phenomena lie in wait within the world of neural fields. Will we discover even more intriguing interactions and patterns in upcoming episodes? Stay tuned to DeepVisus as we continue exploring the fascinating intersection of neural dynamics and computational models in the next chapter. You won't want to miss it. Until next time, keep your curiosity thriving and your mind deeply engaged. This is DeepVisus, where vision meets depth. Thanks for listening.